of us. There's another question here for the panel. Several people during the week have mentioned that the fact that there are plenty of other reasons for formalization beyond is the proof correct. For example, in the last talk, Shankar argued that there's much more about this. And the question is, but don't you think that what is going to happen is that the killer application for formalization is going to become verifying LLM output? And so to prove correctness, proof correctness will become the only question anyone cares about.
No, I disagree. I mean, it's not about that. It's about understanding. I mean, it's not if it's correct. I mean, you also want to understand. I mean, I think even if you do not have AI, I view proof assistants as useful tools. I mean, to manage complexity. Look at the liquid tensor experiments. I mean, there was no AI involved in the project. Also, this other example where a colleague of mine was saying, I only use a result if I prove it myself. This doesn't scale. I mean,
yeah, I too disagree that the killer app is just checking LLM output. Leo already talked about how you can the AI models are actually quite effective for refactoring. This is something that you can use them to aggressively improve presentations, to improve the quality of presentations. And actually, the formalization has many benefits. It's something where you can, for example, perform type checking. So to be able to type check a formal statement is a quick and significant sanity check on things. Now, a lot of LLM output is also informal. That is, you may have things that are opinions. There can be hallucinations also that may be correct, but beside the point. So just because it's formal doesn't mean that it's relevant. And so the real kind of synergy here is that formalisms tend to kind of be brittle. They tend to rely on very, very precise notations, order of things, and so on. The great thing about LLMs and their latent spaces is that they are soft. They're really good at this kind of soft reasoning and being able to make matches that may not involve syntactic equivalence. So that's the kind of thing that I think that fuels the synergy between these two technologies, that you can actually carry out this combination of hard analysis combined with soft reasoning, and some of the hard analysis can be a guardrail for the soft output from LLMs. They can also be reward functions as well. I mean, the other thing that you can have is that having theorem proving as a reward signal also helps in reinforcement learning of these models.
I'm not a speaker today, but may I say something? Can you hear me?
Yes.
yes, I can hear you.
Yes, we can hear you. Yeah, please.
Yes. So I was as a novice. So just maybe some people are not familiar. So let me first introduce myself. I'm Shinichi Mochizuki. I spoke on the second day. So I'm very much a novice with regard to formalization, a newcomer to this field. But in my talk, I emphasized how from my point of view, the importance of of formalization lies not so much in verification. That's one important aspect, but an important and essential aspect. But I emphasized its importance as a communication tool. And so from the point, so first of all, I was impressed by how many, since I'm very much a novice, I was impressed by how this was also emphasized by many experts. This was impressive to me. And in some sense, so there was this statement about it, verification being really the killer aspect, or the somehow the essential aspect. I think of it as sort of being like the use of electricity in all sorts of IT technologies. If you don't have electricity, none of it's going to operate. And so in that sense, you could call it sort of the killer aspect of all IT technologies. But so it's true that you need electricity in order for all of this to operate, but it's much more than electricity. I mean, all the development of information sciences and so on, even though it won't operate without electricity, that's an essential and important aspect of various other aspects, like the communication aspect and understanding the proof, which is very closely related to communication and so on. But so it's an essential aspect that underlies these other aspects. But again, it's just like electricity in information technology. It's far from being sort of the whole story. It's just very, very far from being the whole story.
Yeah, thanks. You're making a nice point to the question that I want to ask, that is extending a little bit what has been asked by somebody in the audience. A little bit more provocative. How would you see mathematics communication working in 5-10 years? We have seen the interactivity of what was it, Lean Verse, I think it was called. We have this similar systems, or also exploring, and you can highlight things in Isabel. Also PVS, you have the proof state that gives you additional information, type hints, way richer ways of presenting a proof and definitions than what we traditionally do when we publish papers these days as a static PDF. How would we do that in the future?
Yeah, I feel like that's why formal mathematics is important, because in formal mathematics is data that can be visualized in many different ways. We are going to have lots of investments in visualization tools. Right? We are going to be able to manipulate these objects, view them from many different angles. It's not far-fetched that in the future we may be working with our friends on a whiteboard, take a picture with our phones or whatever device is available at that time. And the machines are going to start formalizing them, typesetting them. Who wants to typeset using LaTeX? It's a waste of human talent. I mean, you want the machines to do that for us. I feel like the tooling is going to be much better. The visualization tools are going to be much better, and we're going to be able to attack problems that are today beyond our capacity. I mean,
yeah. So these are excellent points. So, one of the things that I find about proofs I've done is that they are actually communication devices to my future self. So a lot of times I go back and revisit proofs that I've done in order to understand how to do something new. These are, the tension in the 70s and 80s used to be that somehow this was getting in the way of what's called the social process, by which mathematics is kind of reaching a consensus. That social process was important to judging whether a proof was right or not. These tools, they do give you a kind of independent verification that's independent of the social process, but they also, in many ways, lubricate the social process. These are things that you can argue over, you can actually change, you can actually look at making changes because it's easy to do. As Leo mentioned in his presentation, if you had to change something in a paper that was from 50 years ago, that's hard to do when it's all on paper. You don't know what the impact of that change is going to be. Whereas here you can actually measure you can actually carry out the change and measure the impact. You can explore mathematics more adventurously. You can try out things that you would never have thought of trying out because failure is always going to tell you something useful when you do that. So these are really the point that it's a communication device. Is really important, that you're not just communicating content, you're actually communicating technique, you're communicating insights from failure, you're communicating patterns, you're communicating the ability to maintain things and make changes. All of these things really give you a kind of industrial scale power in terms of this way of representing mathematics. But at the same time, you can't lose touch with the fact that you're communicating to humans. So the informal aspect of it, being able to present things in ways that are understandable to broad classes of human subjects is critical as well in doing this.
Maybe I wasn't. So my point was also more into the direction, still communicating to humans, but the interactive proof I can explore, as Leo said, proofs, mathematical objects are becoming data, there's visualization. That for me kind of makes reading static papers, so I'm not the writing LaTeX, the reading LaTeX papers becomes more cumbersome because I'm missing those interactive features. That's something that I feel myself since a number of years, more and more. So do we need new forms of mathematical journals that allow me to submit things that are dynamic?
Yes, I think this will happen.
Yeah, absolutely.
I'm looking forward to that future.
Yeah, the thing though I want to warn is that this shouldn't become a form of gatekeeping though. That is, I think, if we start to require this, then, we may be dividing the world into haves and have-nots.
That is definitely a risk, yes. Up. Which one? Yeah, I mean, that's more of a comment than a question. But I think, yeah, let's see if the panel agrees. One thing that happens in paper proofs and longer proofs very often is that if something looks weird, you need to do backtracking, go back in your definitions that you don't know how far you need to go back. That seems to be easier with those interactive tools.
Yes, absolutely. How many times you have been reading a proof and you say, do we really need this hypothesis? You don't know exactly where the hypothesis is used. With a proof assistant, you just remove and you see where it's broke. And when you go there, you say, oh, I can prove this part using a different technique. The hypothesis is actually not needed, right? Or do you convince yourself that it is needed? And I cannot imagine. I think so much superior to understand the proof of this interactivity. But I'm biased, of course.
Yeah, but I mean, for me, the important or the that Shinichi is agreeing as somebody who has not so much experience with formalization. That is something that I like very much, because I'm a little bit blind on that eye, so to speak, just because I'm using those systems for so long. That of course gives one a completely different perspective sometimes.
Yes.
I mean, there was
Let
one
me
question.
mention, let me
Yeah.
go ahead. Can I just address this point a bit from the point of view of education? So Atsupis is a great philosopher of science. He was at Stanford, and from the 1960s, he was running these courses. He was teaching logic and set theory using theorem provers at Stanford, and the experience was not that positive. So what would happen is that the students started to view the technology kind of as a game, and they would essentially be like monkeys at a keyboard. They would just type enough keystrokes to get theorems accepted without actually bothering to understand what they did. Whereas if you look at kind of things that are more demanding in terms of requiring you to actually make sure you understand the argument and so on, then the technology actually does become useful, because what students find is that they can make their mistakes in private. It's not the cycle of where you turn in your proof in a paper and the lecturer says that proof is incorrect because of step 3, and then you're not that much wiser for having learned that your next mistake is in step 7 and so on. So here the ability to actually interact with something, to make your mistakes in private and come out of it being able to communicate the proof in a human way is really, I think, an important part of education as well.
Yeah, I agree, Shankar. And I'm worried about the gap between good and bad students. I view now AI is an accelerator for good students. I mean, if they're really curious, they can go as deep as they want, much quicker. They are not blocked by anything. The AI is there to help them unblock, point them in the right direction, and they keep digging as much as they want. And the bad students now, the problem is that AI is allowing them to cheat. I mean, and they do not. You can literally now today finish a course without learning anything. The AI does all the exercises for you. And I can see the gap increasing dramatically between the bad and the good students. And of course, bad and good are relative. Sometimes the person is not focused. I mean, it's not like it's a bad student. He's not interested in the subject right now. It may be in the future, right? I'm wondering what's going to happen with education. I would love to hear your thoughts. I mean, because this is one thing that I can see AI maximizing. I mean, if you're curious, you're going to find everything you want. If you're not curious, you're not going to learn anything. And there's very little the professor can do, right? The instructor.
I think that is at least something that the colleagues here in the room that are teaching and I are regularly debating. I'm currently planning to update a theoretical computer science module to include theorem provers and do the formalization in there, with the hope that the fact that I can immediately execute my definitions and I can run test cases on my lemmas before I prove them essentially helps the engaged, but maybe students that struggle a little bit more with the formalism, because they can write something and first try out if it is true or not before thinking about proving something. In a year, I can hopefully report if that works or not. That's my hope at the moment, personally. Like using those features that you can explore, and again, this interactive aspect with the mathematical objects, maybe having tests instead of a proof for something, some aspects might hopefully lower the entrance barrier.
Yeah, I agree.
Yeah, I think this is a really significant, again, as we're at this crossroads, I think education is at a crossroads as well, because students might be thinking, if all this knowledge is already going to be available to you at your fingertips, what is the point of actually going through and paying the big bucks to a university to acquire this knowledge when you can get it on demand, when you can just turn on the spigot anytime you want it. And part of the point Leo made is that if you are an expert, these AI models are actually more useful to you. You can actually get more out of them. You can be you can exercise more quality control over them. You can actually persist with them to a point where they are actually in some ways meeting your quality needs. And in that way, it's almost like having a research assistant who you can demand a certain level of quality from. So that's the kind of I think the reason why we really should make sure that students realize that this isn't the kind of way to operate, that you really need to use this. I mean, just like now, because we have certain resources like Wikipedia and so on, we don't really need to have all the information available in our heads. We can look it up, but at the same time, we need to look it up in a way that's we can put this information to use. We can evaluate it. We can actually exercise value judgments on it, and actually see the implications of what you're reading on a Wikipedia page quite dramatically in terms of how it relates to the problem you're trying to address. That is really the reason why we need to make sure that the students do actually have independent critical judgment as the most important thing they acquire in their education.
I have a question to Leo and Shankar specifically. So it's about teaching. So my own experience, and for people who are slightly old enough, so in my case, so for example, I learned set theory, logic, and the beginning of group theory when I was roughly 12 years old. So if you remember, in the 70s, end of the 70s, beginning of the 80s, so there was this American curriculum, and there was this idea of teaching abstract mathematics for young people, right? And then end of the 80s, beginning of the 90s, then there started this tendency where people said, this is too abstract, it's too difficult to teach this stuff to young people. And then they started delaying the teaching of what I call abstract in mathematics to later years. So as a consequence, for example, some of the stuff I'm teaching now at university, I learned when I was at college, even at a younger age. Mm-hmm. So my question is, and this is the problem that we face when teaching mathematics. So the problem now is that the students are not used to the abstract, right? So they are not used, their mind is not used to process abstract structures and so on. So my question is the following. So do you think AI and this new technology can help teach the abstract in mathematics for young people? I mean, 8, 10, 12, and so on. Things like set theory, like logic, like the beginning of group theory, and so on.
I think so. I mean, for example, in your example, you are ready, and your benefits is I can bet anything that you benefit from that.
Yeah, exactly. That's exactly.
AI, I think, will enable us to customize education. You'll not be able to hold someone like you in the future, right? AI will help the instructor. I can imagine the instructor monitoring the students with AI and seeing how much they can push the students forwards, right? I think it is an enabler. It will, right now, the solution is to hold everybody back, right?
Mm.
because people develop at different paces. It's not like the other person is dumber, but it's not ready. Their brain is not ready. We can customize education. I think that's one thing that will happen in the future. Right now, it's not feasible to customize, right? I mean, is a professor, he cannot create lectures, specialized lectures for the different students. But with the help of AI, he can do that, right?
But my precise question also, you as experts, so are you thinking about this stuff concerns things specifically directed to young people, age 10, 12, how to help them understand mathematics and learn mathematics in a more efficient way? So are there any projects in this direction?
I'm not working on any of these projects, but I can see the potential. I can see people building on top of proof of systems and AI and have customized education for younglings. I mean, I can see this happening, and I think it will happen. The benefits is really high. I mean,
thank you. Thanks.
Yeah, so I strongly agree with what Leo said. So I went through the same thing that you talked about in the 60s. There was a movement called modern math. I think that was the thing that you're referring to. And so, I was actually in the first batch of guinea pigs for modern math. And and it's funny, my own children didn't seem to go through that. They had a much less abstract way of dealing with mathematics, and I think you kind of lose a lot when you do that, because part of why you learn mathematics is that you learn to deal with precision and abstraction, and learn to value them to a point where you start to see how they're useful in other fields as well, including even in seemingly unrelated fields like literature. So that's the kind of reason why it's good to learn things that way. But as Leo pointed out, the students have very different learning styles, and we, so far have not been able to accommodate those learning styles. Even the same problem, it turns out, in cognitive science, people realize that the same problem, if you just change the setting for the problem, but don't change anything else, it's abstractly the same problem. The same student would be more motivated to solve the second problem than the first one. You can also find out with these technologies what keeps students engaged. What is it that actually drives their curiosity? You can connect the material they've learned to things that they're already interested in, that they might be interested in. You can actually point them in the direction of things that they could pursue that is tuned to their interests. So I think these are possibilities which we could be exploring in the next 5 to 10 years to literally have this kind of precision education that is precisely targeting the student.
Thanks a lot.
Yeah, there were a couple of questions specific to Lean. I don't want to take too much time on that one, but one that also interests me, I have to say, is the integration with computer algebra systems, and if that will be needed in the future when computations are becoming faster and faster.
Definitely. This is a recurrent topic. We're discussing with the MathLab initiative, the Lean Flow, the MathLab initiative. We want to have stronger integration with computer algebra systems, right? There are people in the community like Bhavik Mehta is deeply interested. He wants to make sure not only you have the integration, but the proofs that are constructed with computational methods, that they will scale, right? Yes, you're completely right. But the good news is that the community is aware and is actively trying to figure out ways to do to implement the integration and make sure these proofs will scale. The checking part, right?
And we have a new question. Shankar mentioned a few times the social context of these tools. The question is if the panel would like to comment on what they would see as the real imagined consequences for the disenfranchisement or that these tools can support.
So I'm not sure I understand the question actually. So what was the last part of it? It sounded like it was disenfranchisement, but
yes,
is that
disenfranchisement
okay.
that these tools can support. Exactly.
So I think the point is that we've talked about the benefits of personalization, but you also have alluded to already that it can also distance some learners. And so, yeah, so how do we navigate that, I think is the question.
Great. Yeah, I'm not sure if Kevin is listening, but he ran a study, and the feedback is like was more or less split. I mean, some students love it, the formal approach. Others dreaded.
I'm listening, and you're you're accurately saying what happened. Yeah.
Yeah. But Kevin, I'm not sure if you agree, but I think some people, this happens because some people they are not. For example, people like you like to solve problems. You told me many times that you get a high when you solve a puzzle, or people that have this kind of connection, like to solve puzzles. They love formal proofs, right? I mean, they view it as a game. They see that's moving stages. But some people are not puzzle solvers. I mean, do you see a connection there? They split because the ones that like puzzles are the ones that love formal, and the ones that do not, they are the ones that dread.
Yeah, I've had quite a funny background because when I was sort of pre-18, I was an able mathematician, and where I spent a lot of my time was solving puzzles because I was involved in this sort of mathematical Olympiad crowd. And I was sort of picked up by these people at 16, and this is all pre-internet. I was being sent puzzles through the post, and I would love these puzzles. I would solve them and send them back all in the snail mail. And this was somehow the way I learned. I learned a lot about mathematics. And then I went to university in this Cambridge system, which is a very competitive puzzle solving. So I went to Trinity College, Cambridge, which was just full of puzzle solvers. And, I wanted to be top of the exams and wanted to be solving puzzles very quickly. And then when I started doing a PhD, my advisor, Richard Taylor, really started to argue strongly and to convince me that mathematics was not about puzzle solving. It was about sort of thinking deeply and theory building, and the other side of the coin that Gowers. And I spent then 20 years of my life sort of really trying to stop myself doing puzzles and spending a lot of time thinking about theory building, and became a theory builder. But then, but I absolutely agree with you that when Lean came along, I was just like, oh boy, this is great. This is like, I'm just straight back to the puzzle solving. The thing about theory building is you spend months on a question, whereas Lean is giving you these highs. It's like, here's a simple problem, and you've got to write code that solves this problem, and there's a fun little. So I think it is appealing to the puzzle solving part of my brain, even though I spent 20 years, 30 years really trying to train myself, for 25 years, trying to train myself to be a theory builder. So yeah, maybe so my experience with students was that I put this stuff in front of 300 people and said, look, we're doing maths in this crazy new way, and I got this really diverse series of reactions. And I think Gihan has had the same. I think Gihan, I don't know if he's maybe he's not. I mean, he's probably around, but
yeah,
I think
I'm around.
Yeah, so I think from talking to you, you also had the same experience. Like some people are just like, this is just the coolest thing ever, and whereas somebody explicitly said to me, You know, if I'd wanted to use computers, I would have done computer science. You know, I came to university to do mathematics, not this. So people do, you know, choose. You know, people have very different opinions about it, and this is why I stopped, you know, teaching it to the first years and then made an optional course for third year undergraduates. But if you were into it, you could come along and learn more. But if you weren't into it, you could stay away. I think some mathematicians are computer phobic. I think Professor Mochizuki in his talk, he mentioned that sort of Japanese, it's probably very late for him right now. I'm not entirely sure. So, you know, he is still around. But he said that some Japanese students were like completely computer phobic, which is kind of funny because my mental model of early computers is that many of them were actually coming out of Japan. Japan was sort of a great developer of sort of computing technology in the sort of 80s when it was all sort of beginning to blow up. But yeah, so I think you do get very different reactions from students.
Well, there are different types of Japanese people, of course. So what I was saying is that the people who come to work on Abelian geometry with me are typically people who are typically interested in Abelian geometry and this includes me, as I mentioned, tend to have this allergy to things like lean. And so
maybe these people are I mean, abelian geometry is this sort of, you know, this very technical theory, and you're typically doing theory building. You're not trying to solve, you know, all these little puzzles. You're sort of developing. You know, the objects are very subtle, right? You know, these objects with these automorphisms, these are very subtle questions, and you're trying to develop a profound understanding of deeply complex objects. And it is very different to just, you know, Shankar showed this very cute proof today of this Cantor Schroeder Bernstein theorem, this bijection. I thought this was great, but this really appealed to the sort of the puzzle. You know, my first reaction was, oh, I want to formalize this proof in lean. I've never seen this proof before. It was a very great proof. But when I've got my Langlands hat on, you know, I'm not thinking about, you know, I'm thinking about a sort of a different kind of mathematics, and maybe Professor Mochizuki's students are sort of much more inclined to be, you know, these theory builders. So maybe it appeals more to the puzzle solvers. I'm not sure. It's an interesting idea, certainly.
Yeah, so that's been my experience as well. There are some people who take to this kind of quite naturally. They enjoy it. They start to view it as a video game in which you're constantly getting these dopamine hits, and you're getting dopamine hits not just from the QEDs. You're getting them from your failures as well. Those aha moments are also giving you these dopamine hits. But then there are other students who say, you know, I'm just comfortable with pencil and paper. This is, you know, not working out for me. But the big danger is this, that, you know, I mentioned this computational Sapir-Whorf hypothesis. So sometimes, you know, the early exposure to formalisms can actually warp your thinking. And in the old days when students came to you having learned BASIC in school, you know, you couldn't shake the BASIC out of them. And, you know, BASIC has all these pathologies and they would persist with these. Another example of this is that Gries and Schneider have this discrete math course in which they tend to favor equational proofs. Their critique is that, oh, you know, people tend to case analyze things much too soon. Let's just not case analyze. Let's just do equational proofs. And that takes you up to a point. It's a nice kind of punchline for maybe a while. But when these students go to the next course, they turn into vegetables. They're not able to actually come out of this particular mold that they've been placed in. And so there is this danger that you know, any kind of monoculture, any kind of you know, immersion in specific formulaic ways of thinking and reasoning can be dangerous. And so it's really important to have a diversity of approaches. It's really important to emphasize the informal presentations. It's really important for students to actually very early on develop their own style for how they think about, create, and present mathematics.
One thing I should say is that I'm of the generation that grew up in the 1970s. And so when I was around 7 or 8, I was very much involved with BASIC. I was very fond of programming in BASIC when I was around 7 or 8, and
it was also my
very,
first programming language. Yeah,
yeah, and then I got involved with the Z80 machine language, and so I was.
My second language was also an assembly language, 6502 assembly. Yeah, we were the same age, right? Yeah,
right. So I went through that phase when I was around 7 or 8 or 9, but then learning about calculus sort of put an end to that phase for me. I just lost interest. But so there are different people who have different trajectories. So.
Yeah, that was also my story. I did a bit of programming when I was about 12 in my case, but then learned more about mathematics, and suddenly that was the end of programming. And I then the next language I learned was Lean. That was my
right. So that's exactly my situation. I haven't been involved with programming since I was involved with BASIC and Z80 in the 1970s. That's
I was competent at computer algebra system. I became competent at Magma. In some sense, that's not really programming. That's just, there's lots of high level functions, and I'm computing modular forms. But I never really thought of that as programming. So as mathematicians have had sort of quite funny programming back. You computer scientists, you just learn language after language, it seems to me. You see lots of these languages in action. But in mathematics departments, there's far less of it involved. So it's much less natural for a mathematician to suddenly start learning. I mean, one of the issues I've had is that they don't know how to use anything, right? They don't know how to install things. They don't know how to use the Windows users. They're the worst, right? If you can't just click on it, you say, oh, we can do this with the command. This is the big problem with Lean 3. Lean 3 is like, oh, great, now fire up a command line. And they're like, well, what's a command line? No, absolutely no, I didn't never seen one before. It's, obviously, especially the Windows users, they don't have a command line. They don't have anything installed. So getting Lean 3 running on their machines was hard work. But Lean 4 has obviously made that. That's one of the things that the FRO has made much easier. Now you can do it without the command line, and I think that was really sort of a crucial thing, to widen accessibility.
Side remark: the grass isn't green on the other side. I think that's just due to the fact that the generation of students that we now have grown up with tablets and phones and don't know what a file system is and hardly use desktop computers. It's more, there's one generation that understood computers well, and now we are back to, we need to explain it very well. It's already late. There's one question that I think makes a nice closing question. We discussed a lot about teaching in the last hour or so. This question is, do you have a clear sense of what it will mean to be a research mathematician in the next 5 to 10 years? What will remain the same? What would be or will be different?
Really hard to predict. I mean, I can answer. I'm not a professional mathematician, but I'm a computer scientist. I don't know what's the answer for a software engineer in the future, for being a computer scientist. Will change. One thing I came to the conclusion how much mechanical things we do every day. I mean, and the AI can already automate writing papers with LaTeX, typesetting. Let's put it like that. Typesetting, make sure that everything's perfect. The slides, everything's perfect. Installing tools, and there's so much mechanical steps we don't realize, and this all are all going away. And for example, for the students, I mean, they don't need to really learn anymore how to install things. The AI will install for them. I mean, they will have all, in a few years, they will all have assistants that will install things, configure things, and nobody will have to spend time doing these mechanical steps that, to be honest, nobody wants to learn. I don't want to learn how to install. For example, I had to install recently. I want my agents to be able to read my email. And I would dread doing this kind of stuff. You have to install many packages, figure out. I just said, figure out yourself. I don't care. And he did it for me. I mean, installed everything. And I see that.
A year ago, I would have said you were crazy, but now, no, right?
Yes. Yes. I think we'll change a lot. I mean, our jobs today, there's a lot of non-creative steps, right? I mean, that's we do because we have to do. I mean,
well, I am a research mathematician, and I'm not really even clear about what things will look like in 1 year, let alone 5 years. It used to be 5 years you could sort of just about predict, but now even 5 years seems I think it's a ridiculous question. Asking anybody what they think that research mathematics will look like in 5 years is a ridiculous question, because I don't think anybody can say with any confidence. But I mean, just let me give you two extreme examples. Let's say AI actually gets to the point where it can start proving new theorems, then then the world will, the whole mathematics will be turned on its head. But here's another. It's not completely impossible. I think it's implausible, but maybe not completely impossible. Maybe it turns out that sort of doing stuff out of distribution just turns out to be impossible for theorem proving. And AI doesn't actually start proving new theorems. It just becomes very good at knowing. It becomes like these mathematicians of 100 years ago. 100 years ago, there were mathematicians that knew everything, or maybe 150 years ago. People knew all of mathematics. So we'll have tools that know all of mathematics and will be competent at doing all of mathematics, but they won't have new ideas. So the field doesn't accelerate as much as it likes. But let's say auto-formalization gets really good. That might really happen. And let's say auto-formalization just starts formalizing the literature. And let's just say it finds a ton of mistakes. Then maybe mathematics in 5 years' time has gone backwards, because now there are all these things we thought we'd proved. And now actually the AI is just like, well, how'd you do that bit? This bit that it says is obvious, this person who's now dead, this thing from the 1950s, how are you going to do that? So like, you just got absolutely, maybe we'll be streets ahead, or maybe we'll actually have gone backwards. Who knows what it's going to look like?
But of course, into that, the challenge is that we have PhD students now who will, in 3 years' time, 5 years' time, etc., be going into that research mathematician place. We have undergraduates who are applying now, who will graduate in 4 years' time into a world we simply don't know what it's going to look like.
Yes.
I think that's really exciting.
Oh, it is absolutely. But in a sense, it's also our job to do that future, that crystal ball gazing, in order to have relevant courses and train them in the skills they need, right? But it's hard because we're negotiating that ourselves right now.
Yeah, on New Year's Day, I could not have predicted March. So.
Yes, that's absolutely right. I mean, auto-formalization has been extraordinary in the last month, and this is going to be the year of auto-formalization, and quite how far it will go, I just have absolutely no idea.
So, but I think the way we do software is been changing from week to week. This is a thing where we're able to put systems together in minutes that would have taken us months, if not years. So I think the way I hope it evolves is in some sense, we all turn into these artists that are building on each other's work. It's like putting together music compositions. You're able to actually bring in tracks from multiple sources, put things together, and you're able to create art out of it, and we spend a lot of time appreciating it. The flip side of it is that we may be looking at a lot of stuff that we cannot evaluate properly, and there's a lot of slop that's being thrown at us, and we're spending all our time trying to sort out where there's kind of a diamond anywhere in this heap of junk that's being thrown at us.
Okay, thanks. Then the conclusion is we just have to experience the future. I would like to thank all the panel members and all the presenters, also all those that are not here at the moment. From my perspective, it was a fantastic 3 days workshop with super interesting and engaging talks. A big thank you to all of you again. And that concludes the workshop. We will send out information towards the end of next week with links to the recordings, maybe a small follow-up. With that, I wish you all a nice and enjoyable weekend.
And thank you very much to the organizers for putting in all that work. Thank you.
Thank you.
Really appreciate
the
it.
Exeter crowd.
Thank you.
Cheers.
Thank you. Bye.
Bye. Thanks.